Okay, hello everyone, and welcome to our webinar, Text-to-Image Diffusion Models. I'm Julie Hong, a sophomore from Wellesley High School and a student volunteer for the Planet Tech program, and I'll be your moderator for today. This event will be recorded and will be available online after the end of our webinar. Please mute yourselves before our presentation. If you have any questions, feel free to enter them into the chat at any time. Our speaker will answer your questions as time permits. Our speaker today is Dejia Xu, a PhD student from the ECE department at the University of Texas at Austin. And his research interests include computational photography, creative vision, and implicit neural representation. He is one of the recipients of the 2022 SNAP Research Fellowship. He will give us a presentation on text-to-image diffusion models. Dejia, we are looking forward to the presentation, so over to you.
Thanks, Julie. Thanks a lot for the invitation, and thanks for the nice introduction. Today I'm it's my great pleasure to talk about text-to-image diffusion models with you. This is a really exciting field at this moment, and a lot of new research is evolving, and I'm really excited to introduce those techniques with you. Let's get started. So, next page. Okay. I'm pretty sure that you are already familiar with all those fantastic images that these large models are capable of generating. So as you may have imagined, these images are not drawn by human beings, but instead are created by computer algorithms. So there are large neural networks that can do this kind of really high fidelity, high resolution images generation for us. And a lot of opportunity has emerged during the process. More recently, people have extended this type of algorithm to work not only on images, but also on 3D and other type of modalities. Yeah, so on this slide, you can see that there are a lot of different artificial creations that can be done using these large-scale text-to-image diffusion models. Not only can they generate images, but also can generate videos or even 3D assets. So yeah, on the bottom left, this video shows a lot of 3D assets that are not realistic and are generated by those algorithms. On the right-hand side, you can see a lot more instances on realistic image editing. You can basically edit an image in whatever way you want. You can even add rabbit ears to the Iron Man, or even change the direction of the objects, whatever you want. So today we're going to take a look behind the scene and see how these techniques are made possible and how we can make use of them. So before we take a look at the text-to-image diffusion models, I want to do a little recap on what are diffusion models. So diffusion models are a type of generative models similar to GAN. So given they are generative models, so their task is to generate images or whatever, videos or 3D. So their job is to generate stuff instead of doing classification or doing segmentation. This is why they are called generative models. And diffusion models are one of the generative models they learn to generate by doing iterative denoising. By saying iterative denoising, we are actually referring to the reverse diffusion process in this figure. So the reverse process means that we start from the left-hand side of this image, of this pipeline. So we start from a Gaussian noise, and then in each step, we gradually remove the noise in this image. As you can see, from left to right, we are reducing the noise level, and the image will gradually become a clean image, as shown on the right-hand side. And on the other hand, we also have a forward diffusion process where we add noise to the image So this is basically the opposite of the reverse process. So instead of removing noise from the image, we are adding noise to images to distort them. Well, next, let's take a look at how these two processes work. So first, let's see the forward diffusion process. So the forward diffusion process is basically adding noise to the image. We know that when we build something, it's relatively easier compared to when we destroy something, is easier than when we build something. So adding noise to image is super easy because if we take a clean image, for example, if X0 here as an example, we can simply mix this clean image with some Gaussian noise, and then the image will become very, very weird, containing a lot of noise. So here we have a very elegant formula. So we can take a clean looking image X0 and a random noise called epsilon. And then we somehow do the mixing or blending to obtain a new variable called xt. So the xt is now containing two components. One is the clean image and one is the noise component. And the authors carefully designed this sequence of alpha t. So alpha t are a sequence of constants that do the weighting between the clean image and the noise. And as a result, we can let the sequence of x0, x1, all the way to xt converge the Gaussian random noise. So you can see here that on the left-hand side, the x0 are clean images, but as we involve more noise to this process, we will gradually shift towards a pure Gaussian noise on the right-hand side. So this is the forward diffusion process. And since we only have one addition equation over there, this job is super easy. We only have to do some addition, and this can be done without the need of neural network. But on the other hand, for the reverse diffusion process, we need to learn to remove the noise from a certain image. And in this case, we are trying to guess what the images will look like. And this job is relatively hard, and there's no perfect formulation for this. So humans are lazy, and we basically design a neural network to do the job for us. How are we going to make this happen? The way we do this is that we can add synthetic noise to the clean images and ask the neural network to guess what is the noise component. So the way we implement this is consider the xt as a noise image. We send it into the neural network and ask the neural network to predict the noise epsilon. And as you can see here, xt composes of two components, x0, which is the clean image, and another component is the noise component, as shown as epsilon here. So the neural network will learn to decompose the given image to two parts. One is the clean image and one is the noise component. That's why we also call this type of neural networks denoising diffusion models. So yeah, these are the two the two major components of the diffusion model. And now you're very familiar with how diffusion models are being used. A natural question is how to train a diffusion model. The good news is that you already know how to train it because the training for a diffusion model is very simple. Let's take a look at this step-by-step algorithm. In each training iteration, we first sample a clean image, which is x0, like we used previously. X0 is a clean image, and then we are going to add noise to distort this clean image. So to do this, we first sample a time step from like uniform time step ranging from 1 to 1,000. And then we are sampling a Gaussian noise, which is the epsilon here. It is sampled from a Gaussian distribution. And then we do the mixing, which is mentioned earlier in our forward diffusion process, that we combine the x0 clean image with the noise epsilon, which is shown in the step 5 over there. So we are mixing the image and the noise component together to obtain a noisy image. And then we send the noisy image into the neural network and ask the network to predict the noise component. So as you can see here, we obtain noise estimation, and then we calculate against the ground truth noise to calculate the MSE loss, and then do gradient descent. So as you can see, within 5 or 6 steps, you already finished the training of this fantastic diffusion model. It's much simpler than we originally expected, right? But you might also be confused, like once we train this denoising network, how do we actually generate images? Like we know this model can denoise images, like remove the noise from the image, but how is this connected with generating those non-realistic images? Here's a visual example, like how the denoiser can help us. So consider, so let's first take a look at the figure on the left-hand side. Consider each location on this 2D grid is an image, and the higher the location is, the better the images are. So consider the image generation process. We are like climbing the mountain. So these 3 hills here are the good-looking images, and we want to somehow shift from the lower level to those high regions. So at each location, if we feed the image into our denoising network, the network is actually providing us with a direction that points to a better looking image, because the denoiser estimates the noise component in the image, and it also points us how to make this image look better, like look more clearer without noise. So you can consider this like as we are climbing a mountain and we have a tour guide telling us which step we should go next. So the denoiser here is our tour guide, and it will lead us eventually go to the top of the hill, which is our good-looking images in the end. This is a visual example illustration for the denoising diffusion process. It is not very accurate, but it tells us rough idea. If you are interested in how this really works, you can take a look at the dense math behind it. It's very interesting, but due to time limit, I'm not going to cover all the details here. So next, I'm going to introduce like why do we need this like iterative refinement process? Why not like generate a good image at one shot? So because we already know that there is a certain relationship between the noisy image and the clean image, because we are distorting the clean image with the noise and obtaining a noisy version of it. So this is the relationship we have between the noisy image and the clean image. Even a noisy image, we can actually estimate the noise component from it using our denoiser. Then the natural question is like, if we already know the noise component, why not just remove it and obtain a good looking image? Well, this idea is attractive, but it doesn't work all the time, because estimating the noise component is far from perfect when we are dealing with very high noise level. And even though the neural network is very large, like there are millions of parameters, you can still not estimate the noise perfectly. So that's why we need iterative refinement. Here I visualize the process for you. So you can see that at the first of the diffusion process, the estimated clean image is very blurry, and it basically contains the overall structure, but never the fine details. And as we lower the noise level, we are gradually adding more high frequency details or textures into the image. And eventually, at the very end of our diffusion process, we finally get a good image. That's how iterative refinement takes place. And hopefully this explains like why we cannot just use one shot and remove the noise all at once. Speaking of this iterative refinement process, there actually is a careful design noise levels strategy, because if we always use very high noise level, the denoiser network is not capable of estimating a very accurate noise. So the idea is that we are reducing the noise level from a very we are cooling down the temperature. It's like at first we have a boiled water at very high degree, and then we are gradually cooling it down to an ice water. And this is how our sampling step works. So we when we generate images from using the diffusion model, we usually call it as sampling. And this is the algorithm of how we sample images from the diffusion model. And this is also very simple. So let's take a look step by step. First, we randomly sample a Gaussian noise. You can see that this is the same distribution as our training. So xt with capital T, it is drawn from random Gaussian, and it basically has no image structure in it. And it is everything is noise. You cannot know anything what's inside it. And we gradually reduce the time step from big capital T to 1. So we are doing the reverse process from the very high temperature, and then gradually reduce the noise level. The T here corresponds to our noise level, and the bigger the T is, noises, the images we have. And we follow this equation on line 4 to gradually reduce the noise level. So when we shift from xt to xt minus 1, we are reducing the noise level a little bit. And overall, like after 1000 time steps, we actually reduce all the noise and come to a clean image of x0, which means that in this image, we have no noise, no artificial noise in it. And x0 is a clean image that we can use for our other tasks. This is the overall big picture of how we inference from the diffusion model. And there are a lot of tricks to make this better, especially when we, on line 4, when we do this noise removal process. The way we shift from xt to xt minus 1 is very tricky because it is basically arbitrary process. You can design whatever noise schedule you want. And there are also a lot of papers discussing about this, but among them, the most popular one is called the DDIM sampler. So DDIM sampler is slightly different from the equation line number 4, like we see earlier. So the above one is DDPM sampler, and the bottom one is the DDIM sampler. DDIM sampler is widely used in many diffusion models, including the well-known Stable Diffusion. And the way DDIM sampler works is also when we shift from xt to xt minus 1, we are also reducing the noise level. And the good thing about DDIM sampler is that you can consider its sampling process as a three-component, three steps. So first, you can see that the first step is predicting x0. So given an xt, it first estimates the noise from this noisy image. And then using these two stuff, we can obtain an estimate of our x0. So we can roughly guess what our clean image should look like. And then we are pointing back towards xt. So like we mentioned earlier, we cannot remove all the noise all at once because the noise estimate is not perfect. So in DDIM paper, the author designed that instead of like removing all the noise all at once, we can add some noise back. So that's what the second component is doing. After we obtain the noise component, we don't remove them all from our image, but instead we only reduce the noise level, which means that we use a special coefficient. I think here it is 1 minus alpha t minus sigma squared under the square root. And so this actually makes sure that the noise level is gradually reducing. as we make a step further in our diffusion process. And last part is random noise. So this random noise basically guarantees the randomness inside our generation. And another good thing about DDIM sampler is that we can actually remove this noise component. So if we remove this noise component, the whole generation process is deterministic, which means that if you sample a starting noise at X capital T, then it has a one-to-one mapping with the final X0 image you get. The good thing about one-to-one mapping is that you can then train, you can then do some knowledge isolation to obtain a smaller model or even a faster model that can do the job better than a big model. So this is why DDIM sampler is very popular. And also there are a lot of other samplers proposed as we speak. Every day on archive, a new sampler will likely to emerge. And this is a area that's developing really fast, and a lot of sampler has their own pros and cons. And there's no perfect sampler for every case. And so due to time limit, I'm going to skip this part and move to the next part. So now you are already familiar with those diffusion models. These models are already capable of generating very powerful images. As you can see here, all those images are generated by the type of diffusion models. They are already performing much better than GANs on large datasets, such as ImageNet, which contains 1,000 class, and it can generate very good looking images. You can see the animals here are, well, to me, I can hardly tell whether they are real or not. The quality is already very good. But our topic today is text-to-image diffusion models. How are we going to connect our text with this type of diffusion models? How do we constrain our generated images to be related with our text? The idea is very simple. We can use some pre-trained text encoder to convert our natural language into those text embeddings. And here, Clip model is such a model that can perfectly do this job for us. But not perfectly, but it's very capable of doing such job. So Clip is a large model that is trained by compressive learning, and it can learn aligned image text embeddings. By saying aligned, we mean that given an image, for example, for a dog, we take its Clip image embedding. It should be very similar to the text embedding for the text dog. So that's why it's called aligned. And the good thing about this is that when we want to calculate image text similarity, Clip embedding is always very helpful. And this similarity actually guarantees that we can generate text, generate images that corresponds to the text we want. So next, let's see how this conditional generation works. So given these text embeddings, the denoiser doesn't blindly estimate noise anymore. Instead, it now knows which region contains more noise or less noise, because it knows to denoise the contents better because they have the text embedding as an input. As you can see in this visualization here, the model can now learn to associate with the text with different regions of the image. And in this way, it can learn better semantics. So consider the image of a bear and a bird. You can see that the word bear corresponds to the region of bear, and the word bird corresponds to the region of birds. So in this case, we can do very fascinating conditional generation syntax because we can use text to control different regions of the image and generate, do compositional generation of different subjects. That's very good part, because when we want to generate large scale images, we usually contain a lot of subjects instead of having one object or so. Or for example, people usually take group photos with different people. And in that case, you will have to like use different tags to mention which regions, which people, and it's hard to achieve this if you cannot associate the text with different region. And there are two other tricks that can help us improve the correspondence between the generated images and the text. I'm going to roughly go through it because these two papers are a bit math dense, but here's the basic idea. So the first paper is called Classifier Guidance. The idea is that they use a classifier to guide the sampling process. So like we mentioned earlier, people are not satisfied with unconditional generation anymore. So previously people like to generate animals or whatever stuff unconditionally. Unconditional means that we don't specify what content we want. We only specify like what class of image we want. And this is very diverse because we can hardly control the content in the generated images. And as the technique advances, people are more interested in like how to do fine-grained control on the content we actually generate. So this is where classifier guidance takes place. The idea is that we design a classifier to like drag the image towards our goal. Like the classifier basically is able to classify whether this generated images is good enough. Is it related to our text, or it has nothing connection with it? So the classifier here is able to push the generated images towards what we want. The way it does the job is that classifier basically estimates the gradient to make the image. So the classifier is asked to provide a gradient. This gradient is to make the image look satisfy the classifier, and this gradient is added to the estimated noise. So the classifier basically provides a way to tune the noise, like modify the estimated noise, so that the image will gradually look become closer in appearance to what we want. And more recently, people have improved this classifier guidance with a new technique called classifier-free guidance. So adopting an additional classifier is somehow sometimes tiring because there's another neural network you have to tune all those coefficients and parameters. And people have designed a new way to get rid of the classifier. So we're still hoping that we can get better control of our contents. But in this time, we don't need a classifier anymore. The way we do this is that we introduce unconditional sampling into the sampling process. So the unconditional sampling here means that instead of using our target tags when denoising, the unconditional sampling requires some null text when denoising. So the null text means that we don't really like constrain our generation. We just let it generate anything possible. And in comparison, we still use conditional sampling to like drive the generation towards our target text. And in this way, we can obtain two sampling results. One is conditional and one is unconditional. And classifier-free guidance here works like a slingshot. So you can see the equation here. It basically does weighted average of these two sampling results. And this slingshot actually amplifies the conditional sampling and makes our generated images more close to our text, for example. So nowadays, classifier-free guidance is very popular because it delivers images more related to the text. And this is also what is widely used in recent diffusion models such as imaging or stable diffusion. Okay, so here's a summary of how to build your own diffusion model. First, there are only 3 steps. First, you get to choose your denoiser model. So usually people just build it with a neural net and a self-attention block. So the architecture is relatively simple. And the second is to choose the training loss. So usually people use the MSE loss, like you mentioned earlier. The training loss is basically a loss to help the model learn to denoise. So we're calculating the MSE loss between the estimated noise and the ground truth noise. And the last step is to choose your sampler. This is used when you test your diffusion model. The widely used sampler is called DDIM sampler, like we mentioned earlier. There are 3 components: the X0 prediction, the XT direction, and the random noise. So now you already know how to build your own diffusion model. It's relatively simple. And next, I'm going to take a few slides and talk about the latent diffusion model. So, I think you might heard of it before. Like, stable diffusion is slightly different from other diffusion models because it is actually diffusing in the latent space. So other diffusion models like imaging or make a scene from Meta, they all learn to diffuse in the pixel space. So their noise estimator works on images. Latent diffusion is slightly different because we are now learning to denoise in the token space. So this token is generated by a pre-trained VQVAE, and it is a lower resolution version of the original image, but it contains more dense information. So like this figure shown here, the red part is the pixel space. So given an image, we first convert the image to the latent Z using our pre-trained encoder decoder. And then the green part illustrates how our diffusion process works. So during our diffusion process, we only operate on the latent space. And we only convert the latents back to images at the end of our diffusion process. As a result, we are only operating in the diffusion in the latent space, so we can save a lot of compute. You might be a little bit confused about the VQVAE I mentioned earlier. So VQVAE is a network that learns to reconstruct the images. It is composed of an encoder and a decoder. So encoder learns to convert images into vector quantized tokens. These tokens are then fed into the decoders to reconstruct the images. So as a result, instead of learning to generate the clean looking images, the latent diffusion actually learns to generate the clean tokens. Yeah. Here's a visualization of the latent diffusion process. So as you can see on the first row, it also resembles the denoising diffusion process. Like in the early stages, the images are very weird, and as the time steps goes forward, we are gradually leaning toward clean images. But it's slightly different from the pixel space diffusion as shown below. So we can see on the below, you can see that in the pixel space diffusion, our model starts from Gaussian noise, which is colorful and high frequency compared to the starting point in the latent space. This is because in the latent space, all the images are generated by the decoder. So the decoder actually guarantees some sort of image quality because the decoder is trained on clean images. It usually generates clean images, and it can hardly generate very high frequency noise. You might be curious, like why we want to use this latent space diffusion, since it is slightly different from pixel space that we are already familiar with. So here are some pros and cons for the latent space diffusion. The first big advantage is that latent space diffusion can work with very high resolution. because the encoder and decoder we're using are actually performing 8 times downsampling. So consider we want to generate an image of 512 resolution. We only have to diffuse in 64 by 64 resolution if we have an encoder that upsamples 8 times. This is very beneficial for high resolution diffusion, because if you want to train a diffusion model that works directly on 512, you will need training samples of this high resolution, and this greatly increases the training burden. Another good thing, like we mentioned earlier, is that the generation is through the decoder. And since the decoder is already trained on some very clean images, the quality is promised. So the decoder can hardly generate very bad images. And this is a good point because the artificial generated images usually contain very strange textures or shapes, and the decoder can guarantee that we at least don't generate very weird textures or noise. However, there are also some disadvantages of this choice of latent space diffusion. The first part is still connected with the decoder. So the performance of this latent space diffusion is connected to the decoder's ability. Like we mentioned earlier, the decoder is pre-trained on some real clean images. So their task was originally to generate clean natural images. So when we want the decoder to work on some non-realistic images, it is actually considered to be out of distribution for the decoder. So it's somehow very important for the decoder to be able to generalize to non-realistic images. Another disadvantage for latent space diffusion is that when we want to use diffusion models as some priors, the latent encoder and decoder somehow distorts the gradient, and it has been shown that the latent diffusion model doesn't work as good as those pixel space diffusion model in those type of tasks. Yeah, so previously that was all I want to share about the technique of diffusion models. Next, I'm going to briefly go through some exciting applications of these diffusion models, like what we can do from using these techniques. The first thing I want to mention is the Dream Boost. It's called personalized generation. So regarding all those previous like exciting generations, people often ask one question like, oh, okay, you can generate all those stuff. How is that important to me? Why should I be interested? Well, the answer is delivered by Dream Boost. So using this technique, you can now obtain personalized generation. You can generate your own subject with diverse background, shape, or poses. For example, you can take a few images of your dog and synthesize pictures of your dog traveling around the world, doing different kinds of activities. People often also use this technique on their own pictures as well. The technique behind it is very simple. So consider like a model that takes us several images, like three to five images of the dog. We also need the corresponding class name. For example, it's dog here. Then we use Dream Boost to fine-tune a text-to-image model in a way that we encode a unique identifier that refers to this object. So by saying unique identifier, we are mentioning the V here. So we want the model to learn that when we say a V dog, we are referring to our dog. So you can see on the right-hand side, when we say a V dog in the beach, we generate the our dog instead of some random dog. Yeah, this is pretty cool because the model can actually associate with what we feed into it with their previous knowledge. And even after our fine-tuning, it can still generate arbitrary images with diverse contents. Here, I'd like to show you another interesting application from the text to image model. So there are a lot of attempts that apply these type of image generation model on video generation. You can see here that these models are capable of doing video stylization or even content creation in terms of videos. Even though you can see that the results are kind of flickering and far from perfect, it is actually a large step ahead in this field, because previously people will need to spend hours doing movie editing, and now we can basically use text to describe our desired videos. Yeah, this model is proposed by Runway ML, and it's recently released. Next, I'd like to introduce some image editing applications. So you can see that since we are using text to image models to generate those images, the images are aligned, are associated with text. So we can use our text to do text-driven image editing. For example, given an image, we can manipulate the object or change the style or contents inside the image, or even we can do image mixing. So for example, on the bottom, you can see given two images, we can select which content or which style we want to use and blend the style together. So yeah, this is the image editing part. And next, I'm going to briefly introduce this Diffusion paper. So this is a very exciting application advancing to 3D generation. And surprisingly, it also uses 2D diffusion models. So this is actually built with a text-to-image model. And you can see that it can generate arbitrary 3D contents that definitely are not real. This is a technique that uses a score distillation loss, which is also considered as a very powerful image prior. And due to the time limit, I guess I'm not going to go through the details of this, but this is a very exciting paper I'd recommend you to take a look at. Yeah, I guess that's all of the parts that I'd like to cover today. And here, I recommend 3 important resources that might help you when you want to implement your own different models or create your own applications or pipelines to do some interesting After Effects. So the diffuser library basically contains all those implementations of the samplers or the UNet, like we mentioned earlier. And the Stable Diffusion paper talks about some basic tricks to help you generate high resolution, high fidelity, high quality images. And the last one is a list of resources for Stable Diffusion, like how to fine tune them, how to inference them, how to combine some images together or do some image editing stuff. I would definitely want to check out this link. All right, next I'm going to go through some questions I received earlier. So if you have more questions,
right.
feel free to put in the chat.
Yep, thank you so much, Jia. I'd like to thank the audience for such a thoughtful set of questions. And like Jia said, if you have any additional questions, feel free to leave them in the chat. All right, let's begin with this question. You mentioned that diffusion models are much better than GANs. Do you want to explain why?
Yeah, well, some people might disagree with me, but for now, diffusion models outperform GANs in like large scale text to image generation. This is because diffusion models are actually have different strategy compared to GANs. Remember that in GANs, we have a generator and a discriminator. So we are training two neural networks all together. First of all, this is not very stable because we have to balance the training process to reach some kind of equilibrium. Another thing is that for GANs, we're trying to generate the images in one shot. So consider in GANs, we basically randomly draw a noise sample and then feed into the network and then obtain a clean image, hopefully. However, diffusion models are slightly different because instead of learning this noise to image mapping directly, we are actually breaking the bridge into multiple steps. Like consider we have 1,000 time steps. We are actually gradually removing the noise step by step. So instead of directly building this connection between two distributions, we break this connection into 1,000 small steps. And in my opinion, this actually lowers the burden for the model. So in each step, it only has to learn to denoise a little bit. It doesn't have to generate the overall content. That's why I feel diffusion models are a little bit promising compared to GANs. Another thing about diffusion model is that since we only need one model to train, we can train much larger model without thinking about like whether they can be balanced or not. Thank you.
All right, thank you. Here's another interesting question. People say that the biggest opportunity in generative AI is language, not images. What do you think of that?
I guess this is a very good question, and I'm not very good at like discussing the future trends. But I feel like there are many opportunities not only in language but also in images, because um, a ChatGPT in terms of language generative AI is already very popular, but people usually perceive stuff in images or videos or other visual contents, and it would benefit a lot if we can augment the reality with not only language but also images. Well, I'm not sure like whether there are more opportunities or not, but there definitely are opportunities.
Yeah, of course. Um, what are some, if any, drawbacks of diffusion models, in your opinion?
Yeah, so regarding the drawbacks of diffusion models, they are actually a big disadvantage of diffusion models because they require 1,000 time step to sample. This is very slow and computation expensive. So consider again, you only have to inference once to obtain a clean image, but in diffusion models, how many steps you have leads to how many times the inference you need to perform. Even though there are recently techniques that learn to distill the diffusion model to farm sampling with only 2 to 4 steps, it is still 2 to 4 times expensive compared to GANs. So that's the main drawback for diffusion models that limit them from being deployed more widely. I guess, however, there are a lot of temps working on this part to speed up the different model. So hopefully it'll be more convenient for us to use in the near future. For example, in this year, I believe.
Absolutely. How do diffusion models unlock new possibilities for generative creativity?
Um, well, I think, well, the main, I'm not sure if they actually unlock the creativity. I think the creativity are from ourselves. Diffusion models are basically a tool to help us visualize our like imaginations or stuff. I guess it's good to see that diffusion models are capable of generating high resolution, high quality images. And I guess it is a way for human beings to do fast prototyping instead of like manually creating all those stuff. That might be promising way.
Of course. All right. Is there a model verification step so that the output data from the diffusion model is what we expect?
Yes. So there is a benchmark proposed by Google called Drawbench. So it basically calculates the image tag similarity between the generated images and the text prompt we design. So in that case, there are certain metrics that quantitatively measure like 10,000 images, whether they are aligned or not. So I guess that's part of a verification step.
All right. Oh, here's another one. Are there any future trends regarding generating images, such as emerging models or different research directions?
Well, there are a lot of like research opportunities in this field because currently it's growing very fast. I guess there are some major directions. First, like mentioned earlier, what we definitely need to speed up the inference of different models because it's currently limiting our ability to deliver more contents to the end users. People develop large models but cannot let everyone to try it out, and it's quite a pity in my opinion. Another direction is to like do some disentanglement of the semantic style and content of the image. So like we've shown earlier in this example, I think. So we can like merge two images and mix them with our arbitrary style or content. I think that's emerging that's a new opportunity for us, which is previously not quite possible. I think diffusion models-based image editing or video editing can be much powerful than we expected. And I believe in the some future that we can do like video clipping automatically with help of those different models.
All right. We have a few questions relating to Midjourney. Can we do fine tuning on Midjourney?
Oh, sorry, I'm not very familiar with
Oh,
whether Midjourney is open source. So if you have access to the checkpoints, model checkpoints, you can definitely do fine tuning on them because like if you have some parameters, you can modify them.
all right. Apologies. Um, I have a question about implementation. So, what tools would you use to implement a diffusion model, and how?
Oh, yeah, that's a very good question. So like we mentioned earlier, there's a diffusers library for, developed by Hugging Face. So they wrap up all the stuff related to diffusion models. For example, the unit architecture, the sampling pipeline, and also the way to do image editing or video editing or image synthesis with diffusion models. The diffusers library basically wraps everything ready for you, and you can like uh, basically compose all the building blocks together to create your own application, which is pretty cool. Um,
Okay. Oh, is the 3D generator as efficient as images?
um, well, that's a very good question. So currently 3D generation using Diffusion takes relatively a long time. So if I remember correctly, they actually need to do 2 hours training to obtain a 3D generation. And this is fairly, I mean, this is relatively long compared to images.
All right. And this is going to be our last question of today. ChatGPT is very hot recently. Do you see any opportunities between chatbots and image generators, like integrated applications?
Yeah, definitely. I think I've seen some applications earlier that use ChatGPT or other GPT methods to generate text prompts to feed into the text image models. I feel maybe these large language models can understand the prompts better and can find some hidden powerful prompts that can do the generation for us, because as we all know that text image generation actually has a lot of tricks, and people usually find some powerful prompts like high resolution 4K into their text to make sure the images obtained are pretty strong. And I feel that using some language model can definitely help us reduce our task. So there are also some recent papers that use GPT models to edit the images. So I think this is also a promising direction where people can use natural language to edit the images. Yeah, I feel there are a lot of opportunities in this direction. And hopefully today's presentation can bring a little bit introduction, and hopefully a few of you will get interested into the development of diffusion models and further develop more powerful tools in the near future. And if you're interested in doing research in this direction, I'm also happy to chat about what are some further opportunities. Thank you.
All right. Thank you so much for your wonderful presentation and your thoughtful answers. To our audience, keep an eye out for our newsletter that is going to be coming out after this meeting or after this webinar. And again, the recording of this event will be online soon. Thank you all so much for attending.
Thanks a lot, Julie.